what happened during the Triassic. Today, we travel back in time to an era of renaissances. The Earth has barely survived the greatest extinction of all time. The world is unrecognizable, chaotic, but it is ready to start anew. It is here that everything changes. The first true modern forests appear. Mammals make their quiet debut, and the very first dinosaurs enter the scene. An era of experimentation, rebalancing, and ambition. But before embarking on a new adventure, don't forget to like the video and subscribe to the channel so you don't miss anything. Thank you, and have a good trip. Imagine a vast, singular continent stretching almost uninterrupted, surrounded by the immense Panthalassa Ocean, covering most of the planet. We are about 252 million years ago, at the beginning of the Triassic, the first period of the Mesozoic. This supercontinent unites almost all the land masses. On the other side, the Panthalassa Ocean stretches as far as the eye can see. Between them, an emerging fault, the Central Atlantic Fault, begins to appear, foreshadowing the future upheavals that will, much later, divide Pangaea into distinct continents. The Triassic is divided into three major subperiods: lower, middle, and upper. These divisions help geologists precisely organize the study of rocks, fossils, and the evolution of life. To be even more precise, the Triassic is also divided into stages with specific names: Induan, Olenekian, Anisian, Ladinian, Carnian, Norian, and Radian, all internationally recognized. The first two belong to the lower Triassic, the next two to the middle Triassic, and the last three to the upper Triassic. These subdivisions allow for a detailed understanding of this complex period. To precisely date these stages, scientists use increasingly reliable methods, such as uranium lead dating. This technique analyzes the transformation of radioactive uranium into stable lead in crystals called zircons. In 2024, measurements on zircons from key sites refined these ages with a margin of error of just 0.06 million years, a remarkable precision in geology. These advances have made it possible to better align each sub-stage of the Triassic with our modern chronology. In addition to radiochronological methods, astrochronology refines our understanding of the Triassic. This technique detects in marine sediments cycles related to variations in Earth's orbit and tilt, discovered by geophysicist Milankovitch. These oscillations influence the climate in the long term and modulate the accumulation of sediment layers. For example, in the Triassic outcrops at Monte San Giorgio, the regular repetition of these cycles in limestone rocks forms a natural metronome to calibrate geological time. Another method analyzes the light isotopes of carbon and oxygen, called delta 13C and delta 18O. Scientists measure these variations in small marine fossils, the conodonts, which once lived in the oceans. This data reveals changes such as water temperature or atmospheric carbon dioxide levels. They are supplemented by laser geochronology, a technique called LAICP-MS. It precisely analyzes tiny mineral grains to extract their age and local chemical composition. Where does the word Triassic come from? In 1834, the German geologist Friedrich von Alberti sought to unify observations made in various regions of Europe. He noticed three recurring types of rocks in certain formations: a red sandstone, a shell limestone called muschelkalk, and Cooper deposits. He proposed the term Triassic in reference to this triple subdivision. This name quickly caught on, helping to connect distant basins. Today, we know that these rocks were deposited while Pangaea was still intact or barely fractured. The Triassic is far from an empty period without major events. On the contrary, recent discoveries continue to shed light on the evolution of dinosaurs and their ancestors. Between 2024 and 2025, several announcements made their mark on paleontology. In Brazil, the analysis of a partial skeleton revealed a silesaurid, a reptile close to the first dinosauriforms. Named Gondwanax paraesensis, it lived about 237 million years, or 261 million years ago, and prompts researchers to reassess the lineage of animals that were precursors to dinosaurs. At the same time, in England, a reptile named Threorditoth chasmatos surprised scientists with its unusual jaw. Paleontologists see in it a novel feeding mode, with cranial adaptations reminiscent of a very selective grasping system. Shortly after, a team from Virginia Tech described a Middle Triassic fish with a turbo jaw, nicknamed Fish VT25. This joint mechanism allowed for a rapid strike to catch swift prey, showing that food competition in the Triassic seas was already intense. Among these strange animals is Garzapelta mulleri, an etosaur. It's a heavily armored reptile discovered in Texas and dated to approximately 225 million years, or 248 million years ago. It had a back covered with thick, bony plates, forming a natural shield against predators. According to paleontologists, this robust armor illustrates the early diversity of defense strategies among terrestrial Triassic animals. These discoveries illustrate the diversity of an era of great upheaval. The Triassic marks the birth of the first dinosauromorphs and ongoing advancements in the sciences to understand ancient Earth. Dating and fossil analysis methods are continually improving, thanks to medical imaging, X-ray tomography, or electron microscopy that reveal the finest bone structures. Between 252 and 201 million years ago, every corner of the planet provides geological clues, from European red sandstone to marine fossil limestones, telling the story of life. The planetary ecosystem is constantly reinventing itself, from the Brazilian silesaurid to the Texan etosaurian. The Triassic is full of keys to understanding reptile evolution and the rise of dinosaurs. It is the beginning of the journey through the Mesozoic, a time when the Earth takes a breath, allowing new life forms to shape the planet for millions of years. In the aftermath of the largest mass extinction, the landscapes of the lower Triassic opened to a world transformed by rising temperatures and geological changes. The freshly ended Permian crisis left deep marks. Regions once lush have become rocky deserts or dusty plains, stripped of their vegetation. The atmosphere is slowly rebuilding itself after the massive increase in carbon dioxide due to ancient volcanic outflows, while the Siberian caldera in the northern hemisphere remains warm. To understand a caldera, imagine a vast basin formed by the collapse of a supervolcano's magma chamber. In Siberia, at the end of the Permian, extreme volcanic activity created this depression, releasing enormous amounts of gas, rich in sulfur and carbon dioxide. These gases intensified the global warming that marked the start of the lower Triassic. Even though this volcanic activity has diminished, resurgences of heat still persist. In these desolate lands, sandstone formations are found, deposited after the crisis. The basal Bunsenstein sandstone designates these typical red layers, caused by iron oxide, a natural rust. At the time, strong winds swept across the arid plains, accumulating dust and sand grains. Water was scarce, but the rare downpours carried many sediments to temporary rivers. Over the seasons, these particles accumulated in successive layers, forming the characteristic red sandstone of the Triassic. Erosion exposes a regolith, a loose and altered layer covering the bedrock. After the crisis, this regolith is rich in heavy metals from the degradation of volcanic and sedimentary rocks, heavily marked by Siberian volcanic fallout. Under torrential rains, these metals concentrate in certain areas, providing geologists with valuable clues to trace environmental variations of that era. Meanwhile, on the Tethesian margin, the edge of the Tethys Ocean in the Eastern Hemisphere, new shallow basins are forming. The margin denotes the underwater boundary between submerged continental zones and deep ocean floors. In these shallow waters, limestone sediments rich in shell debris accumulate. This is called early shell limestone, a rock largely formed by shell fragments of marine fauna gradually recolonizing the shores. This marine shell limestone results from the repeated sedimentation of the remains of marine organisms, such as simple mollusks or carbonate-producing microorganisms. Upon their death, their rigid shells accumulate on the seabed. Over millennia, these deposits compact and cement to form rock. In the lower Triassic, this process is essential for the reconstruction of marine habitats after the massive extinction that decimated underwater biodiversity. In these warm waters, marine circulation remains slow because the differences in salinity and temperature are too low to generate strong currents. The early Triassic atmosphere, sometimes laden with volcanic dust, reduces sunlight and affects plankton production. Despite this, several opportunistic organisms settle. Calcareous algae form the first solid plates, serving as a base for small shells and rudimentary sponges that attach to them. On the neighboring continents, the persistent heat of the Siberian caldera sometimes causes gas releases in geothermal springs, creating hostile environments where few species survive. Humidity is generally lower than in the Permian. With much of the vegetation gone, cloud formation is reduced. Precipitation becomes irregular, accentuating the contrast between dry seasons and rainy episodes. Sediments deposited by sudden floods form irregular strata, evidence of the rare water flows. The gorges carved by these floods reveal layers of cemented red sand, sometimes mixed with pebbles and altered minerals. The lowlands near the Tethys Ocean feature finer deposits, rich in marine organic matter, favoring the future formation of carbonate rocks. The term subsidence refers to the gradual sinking of an area of the Earth's crust, caused by tectonic forces, the weight of sediments, or mantle movements. In the lower Triassic, this moderate subsidence created shallow basins where layers of marine shell limestone accumulate. The neighboring plateaus gradually thin out, while the Tethys Sea sometimes invades these lands during marine transgressions, temporary advances of the ocean onto the continents. In some areas, residual lava flows still traverse fractured zones, forming a moderate volcanic relief, much less intense than at the end of the Permian. Some rivers transport sediments rich in metals and volcanic ash, remnants of residual magmatic activity. In these sometimes surreal landscapes, sand dunes heat under a growingly strong sun, while marine basins slowly accumulate limestone deposits loaded with shell fragments. During the Induan and Olenekian substages, the lower Triassic is a period of profound reshaping. The Siberian volcanic remnants and the gradual resumption of sedimentation shape varied landscapes. Red sandstones, products of extreme climatic episodes and erosion, coexist with the shallow basins on the eastern margin of the Tethys. There, early marine shell limestone creates new habitats for fragile marine fauna, but in full recovery. Despite lands still desertic and a disturbed atmosphere, life slowly begins to recolonize, heralding a renaissance that will develop over millions of years. Here we are at the beginning of the Triassic, between the Indian and the Olenekian, approximately 252 to 247 million years ago. The Earth is emerging from the greatest extinction in its history, the end of the Permian. Ecosystems are fragile, and the climate experiences strong fluctuations, influenced by geological and atmospheric phenomena still partially understood. These variations have a major impact on marine and terrestrial life that current research strives to better reconstruct. It is important to know that the stratosphere, the layer of the atmosphere above the troposphere where we live and where clouds form, was then enriched with sulfur dioxide. Sulfur dioxide, a gas released during violent volcanic eruptions, comes from the fracturing of vast regions of the Earth's crust. At the beginning of the Triassic, the gigantic volcanic outpourings of the Permian continued to release it, increasing the albedo, the Earth's ability to reflect sunlight. A high albedo reflects more rays into space, reducing surface warming. During the Indian and Olenekian, this increase would have caused a cooling of about 3 degrees or 5 degrees, sufficient to slow down the recovery of the first organisms after the extinction. After this cooling period, the Earth experienced a thermal rebound, with temperature increases often stronger than before. This warming is linked to a gradual return of carbon dioxide, a greenhouse gas that traps heat at the surface. This gas likely came from ongoing volcanic activity or the rapid release of carbon stored in organic-rich sediments. This shift from cold to heat profoundly transformed ecosystems, forcing many species to adapt quickly. To understand these fluctuations, researchers analyze precise markers in geological records, such as sulfur delta-34. This isotopic ratio is measured in pyrite, an iron and sulfur mineral often formed in marine environments when bacteria transform dissolved sulfate. In Alberta, Canada, delta-34 oscillations reveal variations in the sulfur cycle, linked to the circulation of sulfur dioxide between the atmosphere, ocean, and biosphere. Sulfur is essential for organisms to make proteins and also influences the climate. These oscillations indicate rapid changes, sometimes accompanied by marine biological and chemical variations. A recent study from 2025 measured the oxygen isotope content, delta-18O, in the fossilized teeth of conodonts, small marine organisms close to the first vertebrates. These fossils, discovered in the Himalayas, reveal a seasonal temperature amplitude reaching up to 14 degrees or 25 degrees Celsius. In other words, the differences between very cold winters and very hot summers were extreme, much more pronounced than today. This unstable continental climate involved an intense water cycle with strong evaporation, cloud formation, and precipitation, causing alternating episodes of severe drought and marked floods in several regions. The flora and fauna of the early Triassic reflect these climate variations. During the Indian and Olenekian, pioneering plants like hardy ferns and small conifers colonized soils often depleted by the Permian crisis. They survived in fragile environments subject to irregular rains, severe droughts limiting growth, followed by heavy rains, causing erosion and destruction of young forests. The vegetation, by fixing carbon dioxide through photosynthesis, influences the climate, but its destruction releases this carbon into the atmosphere, fueling greenhouse gas variations. The terrestrial fauna, not very diverse, already included archosauromorphs, reptiles close to the ancestors of dinosaurs and crocodiles. The climate variations between cold and heat required great resilience from them. In aquatic environments, some amphibians and semi-aquatic reptiles took advantage of seasonal flooding to hunt and reproduce, but their populations declined during dry or cold years. This climatic instability associated with a planet in full transformation, represented a major challenge for the survival and adaptation of species. Recent research highlights the key role of large atmospheric and oceanic cycles in the evolution of living beings. Cooling caused by increased albedo linked to sulfur dioxide slowed the rise of some plants and animals. In contrast, the rapid temperature increase due to carbon dioxide favored the adaptation and expansion of opportunistic species. These extreme fluctuations altered not only temperature, but also sedimentation, water chemistry, and the growth of marine ecosystems. Understanding the climate and carbon cycles around 250 million years ago means realizing that the Earth was not a static world. It responded vigorously to volcanic, tectonic, and biological upheavals. The isotopic variations of sulfur and oxygen tell the story of a recovering planet with powerful internal forces and subject to complex cycles. These markers allow scientists to reconstruct the climate of the time, revealing how life, still fragile after the Great Extinction, survived often unpredictable conditions. These cycles of cooling, warming, and significant temperature shifts show a climate both hostile and changing. They laid the foundation for the reconstruction of lower Triassic ecosystems and influenced the future evolution of species. Analyses of sulfur dioxide and isotopes reveal the main features of this climate, key to understanding the remarkable adaptability of life on an ever-changing Earth. During the early Triassic, in the Induan and Olenekian periods, marine life slowly reemerges. The almost decimated marine ecosystems begin a gradual reconstruction. Among the species that emerge are Claria bivalves, pioneering ammonoids, Ceratitida, and stromatolites covering certain intertidal zones. In 2024, a major discovery in Oman revealed a microbial and sponge reef intact for nearly 250 million years, offering a valuable lesson in resilience and adaptation after this crisis. Bivalves are mollusks with two hinged, often symmetrical shells, living buried in sediments or attached underwater. The genus Claria, considered opportunistic, primarily colonizes disturbed or reconstructing environments where competition is low. After the Great Permian extinction, many marine habitats were empty. Claria quickly occupied these free niches, forming dense populations on the sea floors. Their success is evidenced by their fossils, found on several continents, showing their ability to live in diverse settings, such as muddy bottoms, areas with strong currents, or oxygen-poor places. At the same time, ammonoids of the family Ceratitida appear and diversify in the seas of the early Triassic. Ammonoids are marine mollusks, cephalopods with an external spiraled shell divided by internal chambers. The Ceratitida, the first large ammonoids to survive extinction, are distinguished by simple sutures between the chambers. These medium-sized predators hunt small crustaceans and plankton. Their mobility in the water column and high reproduction rate allow them to quickly recolonize the oceans, taking advantage of the freed ecological spaces. Meanwhile, a major phenomenon develops in the coastal zones of the early Triassic. Dome-shaped stromatolites, created by microorganisms, mainly cyanobacteria, trap and cement sediment particles. These blue-green algae, through photosynthesis, produce oxygen, aiding in the rebound of marine life. After the disappearance of many animals grazing on these bacterial mats at the end of the Permian, stromatolites benefit from reduced predation to develop freely. They locally alter the water and sea floors, preparing the ground for other colonizers. Thus, marine life is slowly rebuilt, driven by the return of photosynthesis via cyanobacteria and algae. The exceptional conservation of the Oman Reef is a valuable testimony to the ecological reconstruction after the crisis. Unlike often damaged fossil fragments, this intact reef reveals a clear history. Indeed, the fine limestone layers, bacterial filaments, and sponge spicules are so well preserved that scientists can reconstruct the biological interactions. The bacteria formed calcareous crusts, serving as a substrate for sponges, which in turn created niches for pioneering invertebrates. This reef perfectly illustrates ecological engineering and marine resilience after the Permian extinction. At the beginning of the early Triassic, landscapes change: red and hot soils, meandering rivers and vast plains, and particularly the gradual reappearance of more complex life forms. During the Induan and Olenekian periods, archosauromorphs emerge, ancestors of the reptiles that will dominate the planet for millions of years. Among them, Prolacerta and Proterosuchus stand out with a morphology adapted to land and environments near water. The term archosauromorph means ancient lizard form. These animals are the ancestors of archosaurs, a major group including crocodiles and dinosaurs. They represent a key branch in the evolution of terrestrial vertebrates. At the heart of this evolution, Prolacerta occupies a special place. This primitive reptile of the archosauromorphs had an elongated skull vaguely reminiscent of certain modern lizards. Although its fossils are often incomplete, the fragments show an agile animal capable of moving on land. It lived near wetlands or rivers, hunting small amphibians and insects. In a climate oscillating between coolness and mildness, its adaptability likely allowed it to survive during the Induan and early Olenekian. Another major actor of the early Triassic is Proterosuchus, an archosauromorph whose silhouette foreshadows that of the first true archosaurs. It had an elongated snout, sometimes adorned with a small outgrowth above the jaws, giving it a unique appearance. Its short legs suggested that it alternated between walking on land and swimming in shallow waters. In a world of winding rivers, Proterosuchus exploited multiple niches: the shores for hunting small vertebrates, and the water to protect itself from the few large predators. The most fascinating discovery about Proterosuchus dates from 2024. Near Harrismith in South Africa, an excavation revealed 20 parallel tracks attributed to this reptile. The team realized that these side-by-side traces suggest a semi-gregarious behavior, a partial form of group living. Until then, it was believed that these primitive reptiles were solitary, hunting and reproducing alone. This discovery opens up a new path regarding their sociability, collective migration, group breeding. Research is ongoing to better understand these behaviors. Alongside these reptiles, some holometabolous insects stood out for their ability to survive in an unstable climate and a low oxygen atmosphere. Holometabolous insects undergo complete metamorphosis: egg, larva, pupa, adult. Among them, the Titanoptera, sometimes giants, could reach the size of a large bird with large wings. But during the Induan and Olenekian, they experienced dwarfism, a size reduction linked to low oxygenation, which made breathing difficult. Fossil wings show that by reducing their wingspan, they better adapted their metabolism to challenging conditions. Imagine vast plains crossed by a great river. The muddy banks retain the footprints of creatures that venture there, soon covered by floods or slight subsidence. Prolacerta hunts small prey, while a group of Proterosuchus roams the shore, leaving the famous parallel tracks that still intrigue specialists. Above, some large-winged insects skim a sparse canopy. The vegetation, marked by the Great Extinction, slowly rebuilds with ferns, giant horsetails, and the first conifers. The rust-colored soils dominate the landscape, with average temperatures around 30 Celsius or 86 degrees, which can vary according to the seasons. The competition between archosauromorphs and other primitive reptiles remained limited after the extinction. The landscape still hosted some dicynodonts, reptiles close to classic lizards, and robust amphibians. Water-related species found refuge in the sinuous rivers, with calm loops where vegetation and aquatic fauna accumulated. The slender archosauromorphs hunted fish and amphibians in these niches. This low competition favored the emergence of new anatomies and behaviors. This era marks the timid beginnings of the expansion of archosauromorphs, laying the foundations for the future dominance of terrestrial reptiles. Over millions of years, the descendants of Prolocerta and Proterosuchus would evolve into great diversity. Some would become formidable predators, others swamp herbivores, and some would specialize in fast running on two legs. Each fossil track sheds light on their movements and behaviors. The parallel tracks in Harrismith, discovered in 2024, show that these primitive reptiles could already group together, revealing an ancient sociability long before the dinosaurs. The early Triassic, far from being just a rebound phase after the mass extinction, sees the emergence of a new dynamic on the emerging lands. The first archosauromorphs settled in the meandering river environments, while insects continued to diversify despite the low oxygen content. Under a blazing sun, on muddy banks cracking underfoot, one can imagine Prolocerta watching a group of Proterosuchus prowling near the water, searching for shelter or prey. Thus begins the story of the archosauromorphs' conquest. During the late Olenekian, the Earth went through a major episode called the Smithian-Spathian Boundary Anoxic Pulse. Imagine oceans impoverished in oxygen over vast areas, disrupting marine life. In these oxygen-poor waters, particular sediments were deposited, black shales. These layers, found notably in Chile, are rich in organic matter trapped in stagnant or little agitated waters. A key marker of this anoxia is framboidal pyrite. This mineral, composed of iron and sulfur, resembles tiny microscopic raspberries, hence its name. In very low oxygen conditions, bacteria use sulfur instead of oxygen to live, producing this particular pyrite. Scientists consider framboidal pyrite as a reliable indicator of anoxic environments, where sulfur becomes vital for microbial life. The molybdenum isotopes measured in these rocks confirm a global drop in oxygen. In global anoxic conditions, the proportion of certain isotopes in the sediments varies significantly. Geologists use these signatures to measure the extent and scope of this deoxygenation, which is not local, but rather a global crisis of the oceans. A study published in 2024 in Science Advances sheds light on the dating and causes of the anoxic pulse. Researchers used astrochronological calibration, comparing cycles recorded in sediments to astronomical cycles, especially the Earth's orbit around the Sun. They showed that this event fits into a long eccentricity cycle of approximately 405,000 years. Eccentricity refers to the more or less elliptical shape of the orbit, which modifies insolation and influences climate and ocean circulation. This key moment of the Triassic, illustrated by the Chilean black shales and molybdenum isotopes, reveals the complexity of the links between atmosphere, oceans, and geological activity. Imagine fragile ecosystems that, despite phases of warming and lack of oxygen, continue to evolve as best as they can. However, the Earth was already preparing for new upheavals. signaling major climatic and ecological changes that would profoundly influence Triassic biodiversity. In the Middle Triassic, between approximately 247 and 237 million years ago, during the Anisian and Ladinian, Pangaea began to break apart. The Tethesian domain at the center of this supercontinent slowly subsides, a phenomenon called subsidence that creates shallow marine basins conducive to the deposition of limestone. In Germany, the formation of the Muschelkalk, or shell limestone, bears witness to this warm, shallow sea where life thrived. Among its inhabitants, sphinctozoan sponges built remarkable reefs. Tethesian subsidence refers to the progressive sinking of the Earth's crust, caused by internal forces and sediment accumulation. During the Anisian-Ladinian, this favored the expansion of epicontinental seas, transforming shorelines into vast lagoons. Warm water dissolves calcium carbonate, which precipitates to form layers of limestone. In the Muschelkalk, there are alternating layers of limestone and marl, reflecting variations in sea levels. Abundant shell deposits bear witness to numerous mollusks and brachiopods, while marine reptile remains reveal a diverse ecosystem. Sphinctozoan sponges are distinguished by their complex calcareous skeleton, with internal chambers separated by walls, offering them a solid structure. In the Middle Triassic seabeds, they formed vast reefs, foreshadowing those that corals would later build. When aggregated, they create shelters for small crustaceans and fish. By filtering water to feed themselves, they contribute to sediment cleansing. Their remains accumulate over time, forming thick layers of reef limestone. Beyond the role of sponges, the Anisian-Ladinian tectonics shaped the geography of the Tethesian domain. Pangaea remained united, but local fractures and vertical movements appeared. Subsidence formed basins, allowing seawater to penetrate continental regions. These incursions deposited carbonate sediments, and sometimes evaporites linked to high evaporation. Variations in sea levels, influenced by climate, result in alternating marls and limestones, indicating recurrent marine oscillations over 10 million years. The study of the Muschelkalk reveals these processes. Geologists analyze the stratigraphic sequences to understand the evolution of environments. Variations in fossils, grain size, and carbonate chemistry provide clues about depth, salinity, and climate. For example, levels rich in bivalves indicate oxygenated water, while evaporate deposits suggest arid periods with intense evaporation. Sponge reefs indicate stable phases with low turbidity and marine temperatures around 20 to 30 degrees Celsius or 68 to 86 degrees Celsius. Subsidence acts as a sediment trap. Inputs from continental erosion, transported by rivers, accumulate in these slowly forming basins. Sometimes, storms lift and move these sediments further offshore, creating mixed layers with marine debris and terrigenous elements. Scientists study these events to reconstruct the chronology and dynamics of the platform. Over time, subsidence deepens the basins. When the water becomes too deep for photosynthesis, reefs decline. Sphinctozoan sponges are then affected. Some adapt, others disappear. During the Anisian-Ladinian period, depth often remains moderate, allowing reefs to thrive over vast areas. The carbonate platforms near the equator benefit from sustained sunlight and a warm climate. This stability, combined with ocean circulation, ensures good water oxygenation. In this context, sphinctozoan sponges proliferate, forming true bastions of biodiversity. This balance is temporary, as the tectonics of Pangaea will soon cause major upheavals. For now, subsidence creates stable habitats, preparing for the future separation of continents. The Middle Triassic thus initiates a slow geological metamorphosis spanning several tens of millions of years. During the Middle Triassic, approximately 247 to 237 million years ago, Earth enters a greenhouse regime. At this time, almost all land masses form the supercontinent Pangaea, which profoundly alters ocean currents and atmospheric circulation, creating varied and sometimes extreme climates depending on the regions. Several factors stabilize the concentration of carbon dioxide around 1/200 parts per million, a high level favoring global warming, and strong seasonal precipitation, called mega monsoons. To understand these 1,200 parts per million of carbon dioxide, remember that this means that out of a million air molecules, about 1,200 are CO2. This rate is much higher than today, where it is slightly below 500 ppm at the beginning of the 21st century. During the Anisian and the Ladinian, this high concentration maintained warmer global temperatures. Although exact estimates are difficult, some researchers believe that the Earth could then be several degrees warmer than today. A study published in 2025 based on the analysis of lithium isotopes provides valuable insights. It shows that the Earth's crust regulates carbon dioxide levels through a mechanism called crustal buffering. When CO2 rises, geological processes such as the chemical weathering of rocks absorb this gas into minerals and sediments. This balance is slow to establish, taking hundreds of thousands to millions of years, causing the concentration to oscillate around high levels. During the Anisian and the Ladinian, this buffering combined with volcanism keeps the atmosphere rich in greenhouse gases for several million years. In 2024, a hydroclimate model developed at the University of Grenoble reconstructs the weather conditions of Pangaea at this time. By combining geological, paleontological, and geochemical data, researchers model the heat fluxes, precipitation, and winds on this supercontinent. According to these simulations, equatorial and tropical lands trigger intense seasonal rains, forming a mega monsoon called Pangaea 2. In some regions of the south and east, these concentrations of rainfall over a few months temporarily transform the landscape, flooding dry plains with lakes and rivers, while a more arid climate persists in the continent's heart. In the Middle Triassic, vegetation begins to diversify due to global warming and increased humidity caused by the mega monsoon. In humid regions, tree ferns and primitive conifers expand, creating new habitats for an expanding fauna. The heat favors the growth of some plants and microorganisms, while others, sensitive to moisture and salinity variations, struggle to adapt. The red soils rich in sediments, resulting from rapid erosion linked to these strong precipitations, still testify to this intense atmospheric activity. The monsoon depends on the thermal contrast between continents and oceans. In the Middle Triassic, Pangaea heats up faster than the seas, drawing moist air from the coasts inland. During the wet season, water-laden winds meet hills and mountains, unleashing torrential rains. Annual floods and inundations reshape riverbeds and transport sediments over long distances. In the dry season, hot continental winds dry out the region, sometimes accompanied by sandstorms. This rapid alternation between humidity and dryness shapes landscapes oscillating between dense forests and temporary deserts. This continental climate dynamic also impacts coastal zones. In coastal basins, rising temperatures and the configuration of Pangaea create shallow seas, where intense evaporation affects some shores, while others receive heavy rains. Over large areas, evaporitic deposits form, a sign of extreme desiccation. Further offshore, atmospheric carbon dioxide alters gas exchanges with the ocean, influencing marine chemistry and the distribution of life in these Triassic waters. The major novelty of the Middle Triassic is the durable stabilization of a high level of atmospheric carbon dioxide, triggering an oversized monsoon. This balance remains fragile over millions of years. Indeed, plate drift, volcanic eruptions, and mountain erosion modify the amount of greenhouse gases. The mega monsoon results from a cocktail of factors. These include the concentration of land in a single supercontinent, intense volcanic activity releasing a lot of gases, and crustal buffering that limits excesses while maintaining a high level of CO2 over long periods. The planetary greenhouse regime of the Middle Triassic contrasts sharply with our current seasons. Almost torrential wet seasons alternate with intense drought periods. These conditions create new biological niches, pushing some species to specialize, while others disappear or migrate to more favorable areas. Rocks and fossils from the era testify to waterlogged soils in the wet season, then cracked by drought, as well as opportunistic forests with resilient foliage, capable of surviving these extreme moisture variations. This chapter of the Middle Triassic reveals an Earth in constant motion, where a high level of carbon dioxide, combined with the unique configuration of Pangaea, creates a planetary greenhouse climate. This balance results from intense volcanic emissions and geological reactions, partially absorbing CO2. The Pangaea 2 mega monsoon, with its heavy seasonal rainfall in the southeast of the supercontinent, is one of the most spectacular manifestations of this upheaval. Cyclic floods, ephemeral forests, and arid plains testify to the extreme variations that shaped landscapes and biodiversity. The stability of CO2 around 1/200 parts per million, ppm, plays a key role in this dynamic, heralding a Mesozoic rich in geological and ecological transformations. In the Middle Triassic, marine life fully resurges. Imagine waters regaining clarity and warmth, allowing countless creatures to recolonize the reefs. After planetary upheavals, reefs reappear as colorful and lively structures. Scleractinian corals, or hard corals, rebuild their skeletons in calcium carbonate, forming architectures comparable to real underwater cities. In Oman and Monte Prada, these reefs gradually cover shallow platforms. Although still distant from modern massifs, they already form the basis of rich and diverse ecosystems. The scleractinian corals of the Middle Triassic play a key role in the marine biosphere by hosting a multitude of organisms. Small crustaceans, sponges, mollusks, and other invertebrates find shelter and food in the nooks of the reef. In these shallow and bright waters, corals associate with microscopic algae, the zooxanthellae. These algae, through photosynthesis, provide essential nutrients to corals in exchange for a stable and protective habitat. This symbiosis, already present in the Middle Triassic, is a fundamental mechanism for the construction and prosperity of the reefs. Parallel to the coral renaissance, the Middle Triassic seas witnessed the rise of ray-finned fish, or actinopterygians. These fish, highly varied in shape and behavior, possess fins supported by thin bony rays, ensuring them agility and stability. A deposit discovered in 2024 in Antofagasta, Chile, reveals their great diversity during the Anisian and Ladinian periods. In marine ecosystems, actinopterygians occupy various niches. Some filter plankton, others hunt small invertebrates or swift prey. This dietary diversity supports the food chain and enhances marine biodiversity. Over time, scientists have discovered varied fossils that reveal the organization of Middle Triassic fish within their ecological network. Some possess powerful jaws, indicating specialized diets, while others have hydrodynamic bodies, perfect for swimming quickly in schools. Some fish, adapted to complex reefs, display large pectoral fins to navigate precisely between corals. This diversity in adaptations demonstrates the remarkable evolutionary flexibility of actinopterygians, a group that will dominate future marine life. A striking example of marine evolution in the Middle Triassic is the discovery in 2025 by Virginia Tech University of a predatory fish nicknamed VT25. Its jaw, known as a turbopivot, combines very rapid opening and closing with a highly mobile joint. This adaptation allowed it to surprise fast-moving prey. In the sometimes agitated currents of the Middle Triassic, where hiding places are scarce, this mechanism was crucial for capturing small fish and fast cephalopods. To understand the turbopivot, imagine a jaw composed of bony pieces articulated like a perfectly oiled lever, allowing a wide and instant movement. The VT25 fish could open its mouth in a fraction of a second, creating a violent suction of water and prey. The fossils show a solid, bony structure, proving that this adaptation significantly improved its survival and reproduction. This discovery also sheds light on the evolution of cranial mechanisms in marine vertebrates, revealing an unexpected level of sophistication at that time. According to published data, VT25 quickly positioned itself at the top of the food chain, benefiting from waters rich in diverse prey. The discovered fossils reveal a thriving underwater environment. Immense schools of small pelagic fish, benthic arthropods filtering particles, precursor marine reptiles, and flourishing coral reefs. Together, these elements depict a revitalized ocean after past crises, where competition is intense, but ecological niches multiply and balance each other. This period marks a climate softening compared to past extremes, with marine temperatures reaching about 30° or 86 degrees in the tropics. This warmth favors reef construction, as scleractinian corals prefer warm, clear waters. In the Middle Triassic, high concentrations of carbon dioxide and the arrangement of continents create shallow epicontinental seas, offering stable conditions for these organisms. Thanks to this climate and geological conditions, corals, actinopterygian fish, and marine fauna diversify like never before. This renewal manifests in various ways. Corals rebuild vast reef masses, offering refuge and nourishment to a multitude of marine creatures. Fish develop a great diversity of adaptations, ranging from active hunting to more tranquil lifestyles. Predators like the VT25 fish refine their techniques, paving the way for future innovations in marine vertebrates. Beyond the reefs, coastal plains, lagoons, and open areas become enriched with life, witnessing a renaissance after a period of significant ecological scarcity. Between 247.2 and 237 million years ago, Earth undergoes a captivating phase in its geological history, called the Middle Triassic. At this time, life on the continents expands rapidly, with archosaurs, including dinosaurs and modern crocodiles, beginning to dominate many terrestrial ecosystems. Imagine vast territories, often warm, covered with large conifers, where formidable predators hunt their prey. In this narrative, we will explore this world in transformation, discovering fauna, flora, and recent scientific advances illuminating this fascinating period. In the heart of the Middle Triassic landscapes, a powerful group dominates the food chains, the Rauisuchians. These robust predators, with their long skull and powerful jaw, are part of the archosaurs, the family of ancestors of dinosaurs and crocodiles. On Pangaea, this still intact supercontinent surrounded by a single ocean, the Rauisuchians reign as imposing lords of the land. Imagine massive animals with powerful limbs, hunting small to medium prey through effective strategies. Though reminiscent of primitive crocodiles, they were likely more agile on land and could run quickly to surprise their prey. Thanks to the fossil traces called batrachopus, paleontologists have reconstructed part of the lifestyle of certain archosaurs. Studying these prints is delicate. One must spot shapes in the rock that are either indented or in relief, and then analyze their organization. The batrachopus traces are fine and regular, suggesting firm steps on muddy or wet ground. These tracks, discovered among others in the Middle Triassic, have shed light on the locomotion of archosaurs and the dynamics of emerging ecosystems. It is likely that the individuals who left these prints were crossing the banks of ancient rivers or alluvial plains, using the vegetation to hide or hunt. The terrestrial life of the Middle Triassic was not limited to the cousins of future dinosaurs. Among the significant advances were the first ancestors of turtles, notably Odontochelys. Long considered one of the first turtles with partial protection, Odontochelys was the subject of an in-depth study in 2024 thanks to X-ray microtomography, a highly precise imaging technique using synchrotron light. Researchers examined its bone structure to understand the formation of its shell. This shell results from the fusion of the backbones, ribs, and dermal elements. This study suggests that the ossification of Odontochelys was less advanced than previously believed. This milestone is crucial for understanding the slow genesis of the armor that, in modern turtles, is essential for their survival. Another striking element of the Middle Triassic is the abundance of coniferous forests, particularly the Vultziales, now extinct, but similar to some modern conifers. These trees dominated the high plateaus, forming immense seas of greenery. The climate, warmer than today, favored their rapid growth. Their dense canopy sheltered a variety of fauna, insects, reptiles, and small vertebrates seeking to escape from the large predators. Sediment analyses, especially from the Ladinian, reveal pollen and spores or sporopollen carried by the wind. In the Ischigualasto Basin in Argentina, samples rich in sporopollen provide a better understanding of the vegetation of the Middle Triassic. Interest in ancient vegetation and fauna led UNESCO in 2024 to designate the Ischigualasto-Talampaya region as a pilot geopark. This site is crucial for conserving fossils and raising awareness about geological heritage. It houses cynodonts, proto-mammals that are both reptilian in their skeleton and mammalian in certain cranial and dental features, illustrating an evolutionary transition. While the archosaurs dominated, these lineages were already paving the way for future biological innovations. During the Anisian and Ladinian ages, Middle Triassic terrestrial life diversifies and conquers new niches. The Rauisuchians, formidable predators, illustrate the rise of archosaurs. Odontochelys, the ancestor of turtles, demonstrates ingenious evolution with its novel defense. The vast coniferous forests of Vultziales offered a rich habitat favoring complex ecological dynamics. The exceptional conservation of sites like Ischigualasto-Talampaya allows the study of cynodont evolution and other terrestrial faunas, providing a fascinating tableau that captivates researchers and enthusiasts. It is fascinating to see how recent research, notably with advanced technologies like X-ray microtomography, challenges our old hypotheses and provides new answers to ancient mysteries. In the future, new fossils, footprints, bones, or plant traces will further refine our portrait of this era of upheavals. The end Ladinian, around 247 to 237 million years ago, stands as a pivotal moment of the Middle Triassic era. Life gradually re-established after past upheavals, but ecological balances remained fragile in the face of temperature variations, oceanic chemistry, and geography. To grasp this period, one must consider a transforming climate, ammonoids subjected to high environmental pressures, and volcanism capable of remodeling biodiversity. We will explore in detail this end Ladinian turning point, unveiling a discrete but significant crisis for oceans and species. Throughout excavations and drills, scientists have discovered that a phase of anoxia occurred towards the end of the Ladinian. Anoxia happens when the oxygen level becomes too low to support the survival of many life forms. This phenomenon leaves distinct traces in marine sediments as the organisms that oxygenate and churn the soil become scarce, altering the composition of the layers. For the end Ladinian, it's specifically referred to as Ladinian anoxia T4, identified through the study of oceanic and continental drills. A major indication comes from the Dolomiti Deep Core project, a deep drill in the Dolomites, a mountain chain in northeastern Italy. These mountains harbor ancient sedimentary layers stacked over hundreds of meters, about 328 to 984 feet, recounting the evolution of Triassic environments. By extracting sediment cores, where each stratum corresponds to a specific period, researchers analyze the chemistry to detect the oxygen content of the water, volcanic activity, and rapid climatic changes. In the case of Ladinian anoxia T4, researchers detected anomalies in delta-238 uranium. This delta term refers to the difference in isotopic composition, the distribution of isotopes relative to a reference. Uranium-238 is an isotope studied in sediments to spot ocean deoxygenation. Uranium distributes differently only in oxygen-poor waters. Significant deviations in this ratio signaled an oxygen scarcity episode during the sediment deposition. This localized anoxia disrupted marine organisms, notably the ammonoids, an extinct family of cephalopod mollusks recognizable by their spiraled shell divided into chambers. These animals occupied various ecological roles, from active predators to particle filterers. During Ladinian anoxia T4, their diversity dropped drastically. About 35% of species disappeared within a few thousand years, or a few miles, a nearly instantaneous span on a geological scale. This loss in biodiversity, less massive than some great extinctions, nonetheless suggests that environmental stresses were already accumulating towards the end of the Ladinian, setting the stage for future imbalances. To understand this crisis, scientists compare the timing of the anoxia, the diversity drop, and global volcanic activity. That's where Rangelia volcanism comes in, a vast igneous province covering western North America, notably Alaska and Canada. These igneous provinces encompass immense volumes of volcanic rocks formed rapidly, evidencing massive and extensive eruptions. A 2025 study suggests that Rangelia volcanism released significant amounts of carbon dioxide and other gases into the atmosphere and oceans. This sudden CO2 injection caused climate warming, disrupting ocean currents and promoting low oxygen zones. Gases like sulfur and methane alter the atmosphere's and sea's chemistry. Dissolved in water, some gases reduce its capacity to hold dissolved oxygen, endangering marine animals like ammonoids, which rely on this vital gas for breathing. From a paleoclimatic perspective, the deep core analyses and isotopic data indicate that Rangelia eruptions could have caused this deoxygenation, along with a disruption of the carbon cycle. Marine organisms fixing carbon, like plankton and some primitive corals, are sensitive to variations in water temperature and chemistry. The stress on a large portion of the fauna affects marine food chains. The disappearance of a third of ammonoids testifies to a rapid change linked to volcanic material excess and greenhouse gases. For specialists, reconstructing these ancient cycles is crucial to better understand the links between climate change, marine chemistry, and biodiversity. While major extinctions are well studied, intermediate periods like the late Ladinian also reveal major disruptions. Some more discrete crises may have escaped the geological records. Thanks to new technologies, particularly the fine isotopic analysis of sediment cores, we discovered that localized or moderate anoxic episodes have influenced the distribution of species in the long term. This nuanced vision of the history of life shows that biodiversity does not always progress linearly between two major extinctions. Small crisis thresholds, such as the Ladinian tipping point, mark the emergence of new dynamics where some lineages disappear while others adapt. The study of Ladinian anoxia T4 and Rangelia volcanism enriches the complex narrative of oxygen fluctuations, extinctions, and evolutionary radiations. It illustrates the sensitivity of marine environments to geological and chemical disturbances and how these forces alter the trajectory of life. Imagine yourself transported about 237 million years ago, at the beginning of the Carnian, a sub-interval of the early late Triassic. The supercontinent Pangaea stretched from pole to pole, dominating the Earth's geography. The interior regions were then mostly arid, dotted with dunes and deserts under a dry climate. But a sudden climate reversal occurs, the Carnian pluvial episode. In 1 to 2 million years, rainfall intensifies, radically transforming these inhospitable lands. This shift marks a major turning point, profoundly reshaping ecosystems. To measure this upheaval, one must know that humidity was suddenly multiplied by 4, where a few hundred millimeters or inches of rain fell each year. Far more abundant rainfall now inundates the soils. Vast deserts transform into marshes, rivers, and lush forests. Despite still high temperatures, this massive influx of fresh water allows new plants and animals to occupy ecological niches that were previously too harsh. This explosion of greenery quickly provides a natural refuge, bringing freshness and abundant resources to species. To uncover the secrets of this wet episode, researchers use palynology, which studies fossil pollen and spores preserved in sediments. A 2025 study reveals that 40% of spores in Carnian deposits come from aquatic plants or very humid areas. This high proportion testifies to a dramatic increase in rainfall and an expansion of marshy environments. By filtering and analyzing these tiny biological traces, scientists quantify the radical transformation of the environment. These observations reveal unprecedented plant biodiversity. Ferns and horsetails, fond of moisture, colonize vast flooded valleys. Conifers, more resistant to heat, occupy drier regions and high plateaus close to marshes. In areas of stagnant water, various seed plants form dense carpets, attracting insects and small vertebrates. The forests become reservoirs of life. Thick layers of leaves and debris enrich the soils, providing shelter and food for many terrestrial species, including primitive reptiles and amphibians linked to wetland biotopes. The underlying cause of this climate change lies in the Rangelia geological province, where intense volcanic and tectonic activity produced immense basalt flows on the surface. Nearly 2 million cubic kilometers, or cubic miles of lava, spread over vast areas. These massive eruptions released enormous quantities of volcanic gases, particularly carbon dioxide, enhancing the greenhouse effect. This increased trapping of heat favored evaporation, triggering a chain of reactions that led to persistent rains. The rise in carbon dioxide and heat leads to a sharp increase in water vapor, a powerful natural greenhouse gas that amplifies global warming. Violent storms form, fueled by intense evaporation over seas and wetlands. Flash floods sweep through valleys, once spared by tumultuous waters. The flooded soils promote rapid plant growth, while lakes and marshes merge into vast interior wetland areas. Although the Carnian pluvial episode lasts only 1 to 2 million years, a brief period on the geological scale, it marks a decisive turning point for the evolution of life. These wet habitats favor the emergence of new animal lineages. Amphibians, present since the end of the Paleozoic, have larger and more stable breeding areas. Reptiles, including the ancestors of dinosaurs, find new evolutionary corridors. The abundance of water and vegetation stimulates primary productivity, enriching food chains and biodiversity. Over time, with the spacing of the Rangelia basalt flows and the slowdown of carbon dioxide emissions, the climate gradually rebalances. Precipitation becomes less extreme, though the Earth remains a warm planet. For organisms thriving in these freshwater and humid forest environments, this golden age comes to an end. Some species adapt to drier conditions or migrate, while others see their expansion hindered. However, the biological innovations resulting from this rainy phase will continue to influence the future evolution of ecosystems. The Carnian pluvial episode illustrates the dual creative and destructive powers of climate upheavals. Born from massive lava flows and volcanic gas releases, it propels the Triassic biosphere into a lush phase. Palynological studies, revealing 40% of spores typical of aquatic environments, testify to this transformation. In a few 100,000 years, barren deserts have turned into rich, wet lands. This brief yet spectacular history underscores the planet's fragility. Even a supercontinent like Pangaea is not immune to major disruptions. In the early Upper Triassic, the Carnian becomes fertile ground for the diversification of life. Pangaea, a vast single supercontinent, is bordered by an immense ocean. Active mountain ranges define some coasts, while warm and cold ocean currents influence the climate. Dominated by warm periods, it also locally experiences heavy rainfall. Coastal plains and riverbanks are covered with ancient conifer forests, tree ferns, and other primitive plants. It is in this humid setting that the fascinating biotic radiations of the Carnian flourish. To understand these radiations, one must first imagine marine and terrestrial life recovering after previous crises. Some groups, having survived, gradually occupy new niches and develop significantly. Among them, the temnospondyl amphibians experience notable growth. This group of amphibians, sometimes massive, varies in size from a human arm to that of a large reptile. Their robust skeleton and flat skull indicate adaptation to aquatic life and hunting in shallow waters. Although amphibians, they differ significantly from modern frogs and salamanders inhabiting marshes, rivers, and wetland areas near forests. Beneath the surface of the waters, small key creatures emerge to understand marine environments, conodonts of the genus Paragondalela. These small organisms, resembling tiny eels, remain enigmatic to paleontologists. Their most common remains are tiny mineralized parts, comparable to teeth, found by the thousands in sedimentary layers. These fragments serve as valuable markers for dating sediments and analyzing past temperatures via their chemical composition. In the Carnian, Panthalassa testifies to a diversification after difficult periods, colonizing shallow inland seas and marking a global reorganization of marine ecosystems. In the varied terrestrial ecosystems of the Carnian, the first Eodromaeus-like dinosauromorphs appear, close relatives of true dinosaurs. These slender and agile creatures, smaller than future large sauropods, explore underutilized niches. Fossils, notably in South America, reveal key adaptations: a structured pelvis, bipedal locomotion, hind limbs longer than front limbs, suggesting a swift stride. On coastal plains, they hunt small prey, facing competition from other dominant reptiles. Their lightness and flexibility give them an advantage for running, jumping, and maneuvering. The presence of these dinosauromorphs heralds the major evolutionary success that would flourish in the Triassic and Jurassic periods. However, some closely related lineages make the distinction with true dinosaurs sometimes blurry. In 2024, a major discovery in southern Brazil sparked great excitement. It is the fossil named Gondwanax paracensis, a silosaurid, a group of reptiles very close to dinosaurs. These animals are positioned between primitive dinosaurs and other archosaurs. The canine-like name reflects the morphology of its skull and its slender quadrupedal posture, reminiscent of the silhouette of a modern coyote or fox. Silosaurids likely fed on a wide range of foods, from small plants to insects and even small vertebrates. Their jaw and dentition suggest an ability to crush or shear vegetation, but they could also be opportunistic. This dietary flexibility, coupled with a robust but light morphology, probably favored their survival in environments with changing climates. The forests of the Carnian underwent humidity variations, expanding or contracting depending on rainfall, while the wet areas, habitat of temnospondyls, could dry up, giving way to more arid landscapes favorable to resilient reptiles. The discovery of Gondwanax paracensis is essential for better understanding the evolution towards dinosaurs. It reveals a gradual narrowing of the morphological gap between certain silosaurids and more advanced dinosauromorphs, filling an uncertain link in the timeline of true dinosaur emergence. This fossil, approximately 230 million years old, shows that these dinosaur-related lineages were diversifying earlier than previously thought. Alongside Eodromaeus-like fossils from South America, it sheds light on a scenario where multiple archosaur lineages evolved simultaneously, occupying different niches before some key groups emerged to dominate successive eras. This biotic radiation of the Carnian embodies the triumph of life in a world in reconstruction, where each morphological innovation becomes a valuable advantage. Between 237 and 227 million years ago, at the beginning of the Carnian, the Earth underwent a key phase of the late Triassic. Marine ecosystems experienced profound upheavals. In this context, coral reefs were reborn along the margins of the Tethys Ocean, offering refuge and new opportunities for expansion to many life forms. At that time, the Tethys formed a vast ocean, separating the lands of the supercontinent Pangaea, whose configuration was very different from today. The warm and humid climate favored the development of corals and other marine organisms. These reefs, made of colonies of microscopic polyps, became true architects of underwater biodiversity. Among these reef builders, the scleractinian corals, equipped with an external calcareous skeleton, formed vast enclosures on the submarine platforms, acting as barriers against currents and waves. Concurrently, hexactinellid sponges fixed dissolved silica in the water and also contributed to the construction of complex underwater structures. The hexactinellid sponges are distinguished by their silica skeleton, a chemical material that gives them both robustness and lightness. This support allows them to anchor firmly on the seabed and filter water to feed on tiny particles and microorganisms. Their presence fascinates paleontologists, as it perfectly illustrates the ecological dynamism of this period. In this vast cradle of life, the first conodont crisis, called the PBE event, captures the attention of specialists. These conodonts are tiny marine organisms close to the first vertebrates, known mainly through their small fossilized dental structures. Very abundant, their remains are easily found in sedimentary layers, making them valuable markers for dating geological formations. During this crisis, conodonts experienced a phenomenon called dwarfism, which is expressed by a decrease in the average size of their fossil structures. Researchers believe this reduction results from harsh environmental conditions, such as a temporary decline in nutrients or variations in salinity. This dwarfism would therefore be an adaptation, a means for these small organisms to better withstand and survive in more hostile environments. In parallel, the analyses of strontium isotopes reveal significant continental dilution in the oceans. Strontium, a natural element present in the Earth's crust and seawater, sees its isotopic ratio vary depending on the source of the sediments. When a large continental surface undergoes intense erosion, it releases large amounts of strontium, which alters the chemical composition of the oceans. According to recent geological studies, this increase in continental input coincides with intensified precipitation, as well as tectonic episodes favoring the formation of new drainage basins. The runoff waters, rich in ions and particles, then pour into the Tethys Ocean, altering the chemistry of its waters. Faced with these upheavals, corals, sponges, and other marine organisms must adjust their physiology to survive and adapt. Behind this apparent prosperity, environmental pressure remains very strong. The increase in sedimentation from emerging lands clouds the clarity of the water, an essential element for corals. Indeed, corals depend on symbiotic algae capable of capturing light for photosynthesis. When water turbidity increases, this vital process is hindered, endangering the survival of coral colonies. Despite these challenges, corals persist, as evidenced by the fossil formations that today reveal their astonishing resilience. Hexactinellid sponges, thanks to their particularly efficient filtration mechanism, adapt well to variations in water turbidity. They thus continue to capture suspended organic particles, actively contributing to marine productivity. Today, these sponges fascinate researchers, as their presence in the geological layers of the early Upper Triassic serves as a valuable indicator of complex marine ecosystems. Associated with corals, they testify to the rich and diverse biological interactions that characterize this period. On the paleoecological level, Carnian events reveal the close interdependence between species. A major disturbance, like the increase in continental freshwater input, triggers a cascade of effects. The conodonts, subjected to this stress, see their size decrease, while corals continue their expansion. At the same time, hexactinellid sponges play a stabilizing role within benthic communities, illustrating how marine ecosystems adapt and evolve in the face of simultaneous climatic and geological pressures. At the heart of these dense marine ecosystems, the involuntary synergy between corals, sponges, and other organisms shapes an undersea landscape of exceptional richness. The relative stability of temperatures, often exceeding 77 degrees near 25 degrees, recreates a tropical climate favorable to this biological proliferation. Nevertheless, resilience mechanisms remain closely linked to geodynamic events, which profoundly influence the fate of this flourishing biodiversity. From our current point of view, it is difficult to imagine what Earth looked like between 227 and 208 million years ago, during the Norian, a period of the late Middle Triassic. And yet, if we could turn back time, we would discover a world in transformation. The continents were slowly beginning to split. This process, known as rifting, gave rise to long depressions called grabens, accompanied by magma injections forming basalt sills in the Earth's crust. To better visualize this pivotal era, let's embark on an imaginary journey to the heart of the Newark Basin in the United States, one of the most emblematic witnesses of this geological dynamic. Before exploring this rifting zone, let's take a moment to understand what paleogeography is. Paleogeography is the study of the positions of continents, oceans, and landforms over geological times. While a few signs of fragmentation were already noticeable at the end of the early Triassic, it was especially during the Norian that deep fissures began to widen. The Central Atlantic grabens we mention here are the fruit of these fractures. They herald the first signs of the disintegration of Pangaea and the future birth of the Atlantic Ocean. The concept of a graben may seem technical, but it's actually quite simple. When a portion of the Earth's crust is stretched in opposite directions, normal faults form. The central area, weakened, subsides, forming an elongated depression, the graben. During the Norian, these fractures acted as true collapse corridors, shaping new landscapes. They also directed the course of waters and the deposition of sediments on a large scale, durably influencing continental geography. In these grabens, one often finds particular formations, basaltic sills. Basalt, a dark volcanic rock rich in magnesium and iron, infiltrated horizontally between the layers of the crust in the form of magmatic sheets. During the Upper Triassic, these intrusions passed through sedimentary rocks, sometimes still wet, causing chemical and thermal reactions, as if the heat of the magma had baked the rock. These structures are evidence of the intense underground activity of the time, fueled by mantle convection, this movement of hot material in depth that slowly tore apart the continents. To better visualize this geological context, let's take the example of the Newark Basin in the northeastern United States, between New Jersey and Pennsylvania. During the Norian, this area was part of a vast rifting system forming a long continental depression, heralding the birth of the Atlantic. The sedimentary layers accumulated there today constitute a valuable testimony of that ancient environment. Lake deposits, evidence of the existence of shallow lakes, as well as traces of an active fluvial network between rivers and inland water bodies, can be observed there. One of the most fascinating aspects of the Newark Basin is the presence of lake varves, thin sedimentary layers formed year after year. Their clear and dark alternation reflects the rhythm of the seasons. Summer deposits fine sediments, sometimes mixed with organic matter, while winter modifies their composition. Like the rings of a tree, each pair of layers marks a year. By studying them, scientists can count the years that have passed and trace climatic and environmental variations over long periods of time. The lake varves of the Newark Basin offer a valuable archive of Earth's orbital cycles related to Milankovich's theory. These cycles, Variation of the orbit, tilt, and precession of Earth's axis influence the climate over long periods. Even without direct weather data for the Norian, the analysis of the thickness and composition of varves makes it possible to detect ancient climatic fluctuations. Thicker layers suggest phases of heavy precipitation, while thinner varves indicate increased evaporation or a lower sediment supply. Research conducted in the Newark Basin has revealed a probable link between tectonic activity and climatic and sedimentary changes. This basin acts as a natural archive, a true witness of the geological past. It shows us a Earth in full mutation, slowly initiating the dislocation of Pangaea and laying the foundations for the future birth of the Atlantic Ocean. This geological period reminds us that major transformations often begin with simple fissures in the Earth's crust. As Pangaea fragmented, rifting gradually outlined the shape of our current world. The archives of the Newark Basin, like those of other similar regions, offer valuable clues for deciphering this planetary narrative. By reading these rhythmic strata, each varve reveals a frozen moment, an ancient memory marking the beginning of a new age for Earth. We are now in the heart of the Upper Triassic, during the Norian. At that time, Pangaea remains united, but geological activity intensifies with vast volcanic episodes. This context is accompanied by a significant climatic phenomenon, the chaotic carbon episode. It is a period of strong disturbances in the carbon cycle, caused by significant volcanic CO2 emissions. Fascinating clues come from conodonts, microfossils, whose tiny skeletons retain traces of these climatic upheavals. To understand the role of conodonts in the study of the late Triassic, one must first grasp what delta-13 carbon is. In geochemistry, the ratio between carbon-12 and carbon-13 is measured, whose nuclei contain a different number of neutrons. Delta-13 carbon indicates the variations in this ratio compared to a reference value. These changes reflect disruptions in the carbon cycle, high production of organic matter, intense volcanism, or changes in ocean oxygenation. During the Norian, a team of researchers analyzed the fossil teeth of conodonts, these extinct soft-bodied marine animals that had small hard elements well preserved in sediments. Their study, published in 2024, Refair's GSL 2024, revealed rapid fluctuations in delta-13 carbon with amplitudes reaching plus 4%. Such variation indicates major disruptions in the carbon cycle, likely linked to concurrent phenomena. Massive volcanic CO2 emissions, a drop or peak in marine productivity, and the accumulation of organic carbon in ocean floors are noted. This study reveals a strong link between isotopic fluctuations and intense volcanic activity during the Norian. Vast magmatic provinces released enormous quantities of volcanic gases into the atmosphere, including sulfur dioxide and carbon dioxide. While sulfur, by forming sulfate aerosols, caused temporary cooling, CO2 intensified the greenhouse effect, leading to prolonged warming. This unstable climatic alternation weakened some ecosystems. Conodonts, sensitive to the chemistry of the water, preserved the traces of these upheavals in their calcified structures. A study published in 2024 in the journal Nature revealed that at the transition between the Norian and the Radian, a new anoxic event struck the oceans. The waters then experienced a severe oxygen shortage, leading to the extinction or migration of many marine species. These phases leave behind black shales, rich in organic matter. Researchers detected characteristic chemical markers such as vanadium, uranium, and molybdenum, which accumulate in oxygen-poor environments, confirming the extent of deoxygenation. During this anoxic episode, numerous deep-sea species found themselves threatened with extinction. Even tropical corals, pillars of biodiversity-rich reefs, were severely disrupted when oxygen or pH levels dropped suddenly. Benthic communities gradually collapsed as the water was depleted of its oxygen. An oxygen-deprived ocean also releases toxic gases, such as hydrogen sulfide, which can rise to the coasts, contaminating terrestrial wildlife and coastal vegetation. This discovery changes our understanding of the evolution of the Triassic. The transition between the Norian and the Rhaetian appears as a phase of significant instability, occurring just before the major mass extinction that marks the end of this era. The confirmation of an anoxic event reinforces the image of a climate marked by sudden crises. Above all, it shows that the Earth-ocean balance is more fragile than previously thought. A combination of CO2, volcanism, and biological productivity is enough to rapidly transform living conditions on a planetary scale. On emerging lands, the flora and fauna of the Norian suffered deeply from climate variations. Well-established coniferous forests alternated between water stress and wetter periods depending on weather conditions. Some animals, like archosaur reptiles, adapted by exploring new ecological niches. Others, more sensitive, depended on stable environments for reproduction. The disappearance of marsh areas, combined with frequent droughts, directly threatened their survival. This chaotic context is part of a global dynamic where volcanism, tectonics, sunlight, and nutrient inputs interact to shape the climate and alter ocean chemistry. By analyzing microscopic fossils and geochemical traces, scientists reconstruct the major episodes that have punctuated life on Earth. For the Norian, isotopic data reveals a period of significant instability, marking a profound imbalance in the Earth system. Between 227 and 208 million years before our era, dinosaurs began their ascent, declining into a wide variety of forms, behaviors, and diets. Imagine a vast, arid continent, dotted with isolated lakes, where vegetation clusters around rivers, and a few plains nourished by seasonal rains. In this setting, the first large carnivores, long-necked herbivores, armored creatures, and small nocturnal mammals, still discrete, but already destined for a unique future, evolved. Let's explore how these pioneers shaped the living world of the Norian. Let's start with the first theropods, these bipedal carnivorous dinosaurs, whose name means beast foot in Greek. One of the oldest is Coelophysis, a slender hunter about 3 meters or 10 feet long, weighing around 20 kilograms or 44 lbs. Its slim body, long tail for balance, and powerful hind legs made it a formidable predator. In the competitive environment of the late Triassic, its speed was a major asset for catching lizards, insects, or small flying reptiles. This agile and efficient model undoubtedly encouraged the diversification of theropods, future masters of the terrestrial food chain. While the carnivorous dinosaurs were developing, the vegetation, grasses, and ferns offered a favorable terrain for the emergence of prosauropods, ancestors of future giant sauropods. One of the most emblematic of the Norian is Plateosaurus. Its silhouette already announced the traits of its descendants: long neck, massive body, and powerful legs. Less imposing than its successors of the Jurassic, it could still reach 8 meters or 26 feet long. Herbivorous, Plateosaurus fed on conifers and vegetation growing near rivers. Capable of walking on 2 or 4 legs, it benefited from great flexibility to move and feed. This adaptability undoubtedly contributed to the success of prosauropods at the end of the Triassic, paving the way for the evolution of future Jurassic giants. At this time, the Dinosaurs, a unique group of armored reptiles closely related to dinosaurs, appeared or strengthened. Their body was protected by a shell of bony plates, covering the back and sides. They evolved near wetlands like marshy banks and floodplains, always close to waterways. Their appearance evoked that of a stocky crocodile, and they were among the largest non-dinosaur herbivores of their time. One of the most recent examples is Garzapeltum welleri, discovered in Texas in 2024. This specimen measured several meters, with a pointed snout and a body covered with solid, bony plates. This discovery shows that in some regions, the Dinosaurs shared the same plant resources as the prosauropods, sometimes even in direct competition. Their armor effectively protected them from predators like Calophysis or other small theropods. This allowed them to maintain stable populations and occupy less accessible vegetative zones. The Norian also sees an astonishing geographical expansion of some primitive dinosaurs. For a long time, Herrerasaurids, among the oldest known carnivores, were considered unique to South America. But a recent discovery in India completely challenges this idea. Paleontologists discovered Malariptor kuti, a dinosaur about 220 million years old in India, then attached to Pangaea. This fossil proves that Herrerasaurids did not only live in South America, but were widely dispersed, likely thanks to the land bridges of the time. This new species, presented by the Indian Scientific Press, illustrates the great adaptive flexibility of the first dinosaurs, capable of conquering vast territories from the early stages of their evolution. While dinosaurs and adosaurs took their place in ecosystems, another group was evolving quietly, mammalian cynodonts. Their name, which means dog tooth in Greek, refers to their specialized teeth and cranial features close to mammals. Among them, Adalabasileus, sometimes considered one of the first true mammals, stands out with a developed brain and a sophisticated inner ear. According to a microtomography study conducted in 2025, it would have adopted a nocturnal lifestyle, thus avoiding diurnal dinosaurs and exploiting ecological niches less exposed to predators. In this rapidly evolving world, the diversification of terrestrial fauna during the Norian relied on a combination of geological and climatic factors. The climate, generally warm, around 30 degrees or 86 degrees, favored the expansion of species into new territories. Sea levels fluctuated, creating continental basins and coastal areas conducive to varied ecosystems. This diversity offered multiple ecological niches where carnivorous dinosaurs, large herbivores, armored reptiles, and early mammalia forms coexisted by adapting their survival strategies. During the Norian, the seas of the Triassic offered an astonishing, often overlooked world. Imagine sailing above warm waters at 28 degrees or 82 degrees on the surface, bathed in light and rich in coastal nutrients. On the continents, Pangaea still dominated the planet, but beneath the waves, marine life followed its own evolution, marked both by great diversity and by early signs of ecological fragility, revealed today by geological and fossil records. Let's focus first on the true masters of the Norian seas, the ichthyosaurs. Their name, meaning fish lizards, reflects their streamlined shape, with an elongated snout ideal for hunting. Fast, agile, and capable of deep dives, they dominated the ocean as top predators in the food chain. Their diet consisted of fish, various cephalopods, and sometimes smaller marine reptiles. In this marine world, some studies mention Prionosuchus tardif, a still controversial species. Until now, the genus Prionosuchus was associated with large semi-aquatic amphibians of the past. but recent discoveries suggest that a lineage may have survived until the Norian, exploring new ecological niches. Fossils found show a robust skeleton and vertebrae adapted for swimming, possibly indicating an aptitude for prolonged diving. Although this hypothesis remains debated, it enriches the portrait of an ecosystem where, alongside ichthyosaurs, other massive creatures played an active role in the food chain. Among the notable discoveries of the Norian, the fossilized giant squid found in Nevada in 2024 draws attention. This cephalopod features a radula, a sort of raspy tongue, far more developed than those of species known until now. Normally lined with small chitinous teeth for shredding food, it was elongated here, possibly for capturing large prey or piercing solid shells. This anatomical anomaly could reveal a still poorly understood evolutionary stage of Triassic squids. Diving into the Norian seas means discovering a bustling ecosystem. Primitive corals, sponges, and calcareous algae formed reefs conducive to rich biodiversity. Bony fish, ancestors of many current species, swam in tight schools, ideal prey for marine predators. One would witness a hunting ballet, fast ichthyosaurs tracking by sight, and giant squids using their oversized radula to trap in the darkness. Each species had to fight for its survival in this highly competitive environment. Despite this abundance of life, some geochemical clues suggest a gradual change in the oceans towards the end of the Norian. By studying calcium-48 isotopes present in limestone layers and fossil shells, researchers access information about the water chemistry of the time. Simply put, the more pronounced the isotopic imbalance, the more it indicates a rise in carbon dioxide in the atmosphere, leading to ocean acidification. Recent analyses clearly show this shift, a signal of an ongoing chemical upheaval. This acidification could be explained by the violent volcanic eruptions of the late Triassic, which released significant amounts of carbon dioxide into the atmosphere. This gas, when dissolving in the ocean, altered the water chemistry, affecting currents and the distribution of nutrients. Primitive coral reefs, sensitive to temperature and acidity variations, were particularly affected, weakening the entire marine balance. For researchers, calcium-48 isotopes act as a warning signal, revealing an increasingly hostile environment for marine life. For top predators, more acidic water meant fewer prey. Even the powerful ichthyosaurs, despite their broad distribution and adaptability, were not completely spared. As for the giant squids, which were thriving according to the Nevada fossil, their survival also depended on the abundance of their prey. If acidification had prevented some mollusks from forming their shells, the entire food chain could have been disrupted. At the end of the Norian, just before the Radian, all evidence points to increasing pressure on marine life. Between volcanic eruptions and sea level fluctuations, several factors destabilized established balances. The dominant ichthyosaurs and other marine reptiles were approaching a new breaking point. Measurements of calcium-48 bear the trace, a silent memory of a tipping ecosystem. Despite its apparent richness, the Norian marine biosphere already showed early signs of a difficult transition. The ichthyosaurs, the mysterious late Prionosuchus, and the giant squids with elongated radula testify to the incredible diversity of this era. But chemical analyses reveal that an imbalance was on the horizon. The calcium-48 indicates a progressive acidification, highlighting the fragility of ecosystems in the face of environmental changes. This marine past reminds us that a simple shift in conditions can unbalance even the most powerful creatures. At the very end of the Triassic, during the Radian, between 208 and 201 million years ago, Earth entered a critical phase, sometimes called the pre-terminal crisis. It is one of the major turning points in its history. The supercontinent Pangaea remained largely united, although cracks began to appear. Several phenomena then converged: massive CO2, carbon dioxide emissions, chemical disturbances including halogens, reduction of the ozone layer, a rise in UVB, and an anoxic crisis in the oceans. To better understand this period, let's examine these events step by step. Let's start with carbon dioxide, a key greenhouse gas in the climate. During the Radian, its concentration reached up to 2,500 ppm, an exceptionally high level, indicating a marked global warming. This increase was amplified by intense volcanic activity, especially in the future Atlantic Ocean region. It was there that the Central Atlantic Magmatic Province, with its explosive eruptions, projected massive plumes into the stratosphere. The gradual opening of Pangaea in this area released enormous volumes of lava and gases in a short time, causing a profound climatic imbalance. In parallel, large quantities of halogens like chlorine and bromine were released by the volcanoes, contributing to the destruction of the ozone layer. This natural barrier, essential for filtering UV rays, would have been reduced by half during the Radian. The result? An influx of UVB rays reached the surface. In plant spores fossils, scientists identified typical malformations from excessive UV exposure. These signs of environmental stress show that plants were already weakened, an impairment that could, by itself, unbalance the entire food chain. In this fragile context, marine life underwent profound upheaval. A study published in 2024 confirms the existence of an oceanic anoxic event at the Noarian-Ratian boundary. This was a period when the seafloor critically lacked oxygen, making the water uninhabitable for many fish, mollusks, and invertebrates. Sediment cores taken from several regions show abnormally high levels of vanadium and uranium. Their strong presence in the sediments indicates that the water was almost unbreathable for marine fauna at that time. These anoxic crises, associated with the rise of CO2, create a vicious circle. Warming slows ocean circulation, preventing oxygen from reaching the sea floor. Thus, entire ecosystems collapse. Corals, sponges, and other reef organisms disappear locally, leaving dead zones that are difficult to recolonize. This phenomenon, accentuated at the end of the Triassic, fits into a long series of climatic disturbances that had been ongoing for millions of years. On the emergent lands, the rise in CO2 and the decline in UV protection disrupt forest growth, soil health, and food availability. Some herbivorous species see their resources diminish, forcing rapid adaptation. The most resilient animals, including some dinosaur lineages, manage to maintain stable populations despite an unstable climate. This resilience will be decisive at the end of the Triassic, when extinction hits the most fragile groups. It is important to remember that this pre-crisis phase spans hundreds of thousands of years. The eruptions, the accumulation of gases, the loss of ozone, or the reorganization of marine environments are progressive. Yet, on a geological scale, these upheavals remain rapid, profoundly transforming the planet and redefining the evolution of life. Researchers continue to explore the multiple dimensions of the end of the Triassic. Thanks to technological advances such as high-precision geochemistry or modeling of paleotemperatures, our understanding of the terminal pre-crisis is improving. This interval reveals powerful interactions between volcanism, tectonics, and the biosphere. Deformed spores, increasing ocean stratification, and certain sedimentary deposits confirm that a global shift is underway, heralding a massive extinction. In summary, the Rainfall ends in a chaotic climate, an atmosphere saturated with carbon dioxide, oceans in severe hypoxia, and a biosphere assaulted by intense ultraviolet radiation. The central Atlantic pliniates, by releasing halogens, weaken the ozone layer, while high levels of vanadium and uranium confirm a critical lack of marine oxygen. This terminal pre-crisis foreshadows a major extinction. In this context, dominant species falter, and only the most resilient or opportunistic are already beginning the transition to the Jurassic world. In this final phase of the Upper Triassic, called the Rainfall, the Earth goes through one of the most significant mass extinctions in its history. For a long time, the exact causes of this abrupt disappearance, affecting nearly half of marine genera, raised many questions. But thanks to sediments, isotopic data, and correlations between fossil sites, researchers have been able to reconstruct a complex scenario, punctuated by 3 successive episodes known as triple pulses. These 3 critical phases are known by the following names. First, the pre-Pliens-Bacchian event, then the Kalk-Schiefer Zone horizon, and finally, the basaltic effusion peak associated with the Central Atlantic Magmatic Province, abbreviated as CAMP. The sequence of these 3 pulses deeply disrupted the biosphere, leading to the extinction of about 50% of marine genera known at that time. To understand the mechanisms behind this triple assault of nature, we must first return to the pre-Pliens-Bacchian event. This unfamiliar term describes a phase of upheaval occurring just before the Pliens-Bacchian, the second stage of the Lower Jurassic. This period marks a major transition on geological and paleontological levels. Signs of change are already visible in the oceans and atmosphere. Marine deposits show significant chemical fluctuations, notably a variation in carbon dioxide and imbalances in the carbon cycles. The fossils of ammonites and conodonts, sensitive to temperature and oxygen variations, reveal an initial ecological stress, announcing the end of the Triassic. The second episode, called the Kalk-Schiefer Zone horizon, refers to a layer of limestone and shally sediments, marking a new global disturbance. These strata show isotopic variations of carbon and oxygen, signs of rapid climatic oscillations. During this period, marine groups such as primitive corals, bivalves, or certain fish undergo intense evolutionary pressure. Reefs, already slow to form, struggle to survive amidst chemical upheavals and declining dissolved oxygen. The most fragile species, particularly those living on the surface or in specialized habitats, quickly go extinct, worsening the biodiversity crisis. This third episode, a true coup de grace, is linked to the massive lava effusions from the Central Atlantic Magmatic Province, at a time when a primordial ocean was opening between separating continents. These gigantic basalt flows, often called traps, when they form thick, stacked plateaus, would have released immense quantities of magma. Volcanic gases, notably carbon dioxide and sulfur dioxide, profoundly altered the atmosphere, intensifying the greenhouse effect and causing a sudden warming. This Camp Basalt's peak marks the height of volcanic activity, as marine life, already weakened, definitively falters. According to a model published in 2025 on the scientific platform Earth Archive, these events are believed to have caused a sharp rise of 6 degrees Celsius, or 11 degrees, in less than 30,000 years, a blistering pace on a geological scale. This elevation would be due to the immense quantities of greenhouse gases released by the volcanic flows and tectonic rifts of the Central Atlantic Magmatic Province. Researchers describe a climate runaway comparable to a cogwheel. The heat releases even more gas, accelerates the decomposition of organic matter, and worsens the greenhouse effect, an uncontrollable spiral, fatal to ecosystems already weakened. The most direct consequence of this warming is the emergence of anoxic zones where oxygen becomes scarce. When deep waters cease to be mixed, asphyxiation spreads to many marine organisms. Calcareous shell-producing animals, such as mollusks or corals, suffer from ocean acidification due to the massive absorption of carbon dioxide. This chemical imbalance disrupts their ability to calcify. Gradually, these upheavals cause a hecatomb. Some species become extinct, others decline drastically. It is estimated that about half of marine genera do not survive this ecological crisis. On the continents, the situation is hardly better. An atmosphere laden with volcanic gases, an unstable climate, and rapidly changing landscapes make survival difficult. Ecosystems, already fragile under an unstable climate, cannot withstand these upheavals. Forests, sensitive to changes in temperature and precipitation, suffer the effects of acid rain, heat, and lack of water. Food chains, dependent on vegetation and small herbivores, become disorganized. By the end of the Rainfall, only the most adaptable animals, such as some dinosaurs with varied diets, manage to survive, unlike specialized aquatic reptiles and amphibians. Despite its dramatic scope, the end Triassic extinction occurred in 3 successive major waves that progressively annihilated already weakened species. The fossil record reveals these crises in distinct geological strata, marked by a steady decline in diversity until the disappearance of entire groups. The fatal blow seems linked to volcanic activity of the Central Atlantic magmatic province, which released enormous quantities of carbon dioxide and toxic gases, leading to rapid and irreversible warming. Today, this phenomenon highlights the vulnerability of ecosystems to rapid climatic changes. The model published on Earth RCIV in 2025 reveals a close correlation between the intensification of volcanism, temperature variations, and the collapse of biodiversity. This understanding helps explain why marine organisms were decimated, while some terrestrial groups, more mobile or adaptable, survived to colonize the Jurassic. Thus ends the Triassic, carried away by powerful geological upheavals that sealed the fate of dominant species for millions of years. The Rainfall, the final act of this era, reminds us how vulnerable life remains to the Earth's upheavals. Volcanic emissions and global warming do not belong solely to the past. They are part of a larger dynamic capable of triggering deep ecological crises. During the Rainfall, Earth undergoes a period of marked instability. The landforms slowly erode, shaped by winds laden with particles, irregular rains, and a changing climate. The landscape alternates between alluvial plains, marshes, sparse conifer forests, and vast sandy expanses, remnants of ancient inland seas. In this often arid environment, but traversed by winding rivers, life persists. Several faunal groups develop survival strategies, revealing an astonishing capacity for adaptation. Among the terrestrial fauna of the late Triassic, a group of dinosaurs stands out for its resilience, the Calyphysoids. These primitive theropods, bipedal carnivores, move on their hind legs. Medium-sized, they feature a slender body, long slender legs, and a rigid tail used for balance. Their narrow skull, equipped with jaws filled with sharp teeth, resembles that of an agile hunter. In an unstable environment, they seem to rely on their speed and agility to escape larger predators and exploit a variety of available prey on the continents. At the same time, the phytosaurs are experiencing a marked decline. These semi-aquatic reptiles, often mistaken for large crocodiles, dominated the Triassic wetlands for millions of years. With long snouts, powerful jaws, and armored bodies, they ruled the rivers and lakes. But their strong ecological specialization, combined with the upheavals of the Rainfall, jeopardizes their survival. The disappearance of many marshes, the transformation of waterways, and the scarcity of prey weaken them. Gradually, these amphibious predators become extinct, almost entirely leaving the fossil record by the end of the Triassic. In parallel, another group attracts the attention of paleontologists, the mammaliaforms, ancestors of mammals. Their anatomy already shows typical traits, such as specialized dentition or an evolved middle ear. In a world populated by large reptiles, these small animals, often weighing less than 500 grams or 1 llb, find refuge in burrows, adopt a varied diet, and develop nocturnal behaviors to escape predators. Their small size allows them to hide easily, limit their energy needs, and exploit resources overlooked by the dominant species of the late Triassic. This cohabitation is accompanied by strong pressures due to geological upheavals. The Earth goes through cycles of rising and falling sea levels, leaving marks in lacustrine and fluvial sediments. The seasons become more pronounced than in the Middle Triassic, with unstable temperatures and sometimes intense rains. The conifers, still dominating several fragmented forests, suffer from seasonal fires. Some paleobotanists believe that these fires, fueled by the changing climate, created new habitats where small mammaliaforms find refuge. In this constantly changing context, the study of fossil tracks reveals the diversity and lifestyle of late Triassic fauna. In 2024, a major discovery occurred in Zion National Park in the southwest of North America. This is a site called Mega Track Site. On this vast expanse, more than 14,000 dinosaur tracks have been found in lacustrine argillites, rocks formed by the solidification over millennia of ancient clay sediments deposited at the bottom of a lake. Exploring this national park, one imagines the colossals trotting in small groups along the shores, perhaps indicating social life or coordinated movement. Their parallel tracks form real fossil highways, each footprint telling of a fast or cautious stride. This profusion of traces illustrates the vitality of these dinosaurs, capable of hunting small tetrapods, arthropods, or even modest reptiles in wetland areas. It is also possible that they shared these habitats with the phytosaurs before the latter's disappearance. As one walks through this vast protected site, a great variety of tracks can be observed, reflecting the presence of young animals with light steps and heavier adults. For paleontologists, each footprint is a piece of a vast puzzle: the orientation of the feet, the length of the strides, and the depth in the dry mud. Thanks to surveys and photogrammetry, they reconstruct behaviors and soil conditions. In this ancient lacustrine environment, the force of the water, the clayey nature, and sedimentation favored conservation. The exceptional density of the tracks suggests a frequently traveled passage, perhaps a shore attracting a great diversity of life. At the very end of the late Triassic, the oceans underwent profound changes, heralding major forthcoming upheavals. Several key phenomena occurred simultaneously: the final rise of conodonts, the disappearance of certain ammonoids like Phyloceratites warthae, the intense activity of basalt flows from the central Atlantic magmatic province, and the adaptation of small microscopic creatures such as Radioglaria minor. A marine biomarker named BRG-DGT also provided valuable clues about these subtle environmental transformations. To understand these phenomena, Let's focus on conodonts, small marine organisms from the Paleozoic and Mesozoic eras. These denticulated structures, a few millimeters or a fraction of an inch long, would belong to a primitive group close to vertebrates without complex jaws. Their fossilization in the form of microscopic dental elements reveals the chemical composition of the oceans over time. During the Rainfall, conodonts experienced a final diversification before declining and almost completely disappearing. This phenomenon reflects an unstable oceanic climate and changing conditions, leaving little chance for sustainable adaptation. This instability also translated into the gradual disappearance of certain ammonoid lineages, notably the Phyloceratites worthii. These marine mollusks, related to ammonites, lived in a spiral shell and swam thanks to an internal buoyancy provided by gaseous compartments. Highly specialized, Phyloceratites were sensitive to sea level variations and ocean acidification. Faced with an increasingly acidic and nutrient-poor environment, they could no longer maintain their populations, leading to their extinction. Their decline heralded a major ecological degradation. One of the great oceanic upheavals came from the basalt flows of the Central Atlantic Magmatic Province, or CAMP. This intense volcanism caused immense basaltic lava outpourings on land. As these flows cooled, they released large quantities of carbon dioxide dissolved into the oceans, causing a progressive acidification. This change weakened calcareous skeleton organisms, like those that build shells and structures. These animals need neutral or slightly basic waters. When the pH drops, their biochemical exchanges become complicated, and forming new shells becomes difficult. Acidification affects not only shell-bearing animals, but also marine food chains. Microorganisms and primary producers react to changes in temperature, light, and chemistry. In this context, Radioglaria minor, a planktonic microorganism, stands out by using low concentrations of nitrate. These radiolarians, unicellular with a siliceous skeleton, feed on organic matter and small organisms. The ability of Radioglaria minor to tolerate these conditions shows how microscopic biodiversity adapts in the face of resource scarcity, illustrating the resilience of planktonic microfauna in extreme environments. Nitrate, an essential salt containing nitrogen, is a key element of proteins and nucleic acids. In the oceans, it is produced by specialized organisms or complex chemical reactions. When a marine habitat lacks nitrates or its chemical balance changes, only the most resistant or opportunistic microorganisms survive. Radioglaria minor illustrates this adaptation. It is able to thrive in nutrient-poor environments, surviving while other, less flexible species disappear. To better understand these changes, scientists use a biomarker called branched glycerol dialkyl glycerol tetraethers, BRGDDGT, organic compounds produced by certain microorganisms in soil or water. These molecules integrate into sediments and are preserved over long periods. By analyzing their structure, researchers reconstruct the evolution of temperature, acidity, and other environmental parameters. During the Rainfall, this biomarker reveals gradual changes in microbial activity, reflecting episodes of stress linked to acidification, water warming, or disruption of nutrient supplies. This fragile balance between acidification, shrinking ecological niches, and the emergence of adaptive microorganisms heralds a major transition. The final distribution of conodonts, the disappearance of Phyloceratites worthii, and the adaptation of Radioglaria minor paint a picture of oceans in profound transformation. The basaltic flows of volcanism from the Central Atlantic Magmatic Province are the main driver, altering the atmosphere and marine chemistry. While some groups disappear, others develop new traits, demonstrating their ability or inability to survive in this changing world. With hindsight, this complex dynamic reveals the beginnings of a global change beyond the Triassic. For researchers, it is difficult to separate causes and consequences. Volcanic emissions, biological evolutions, climate, and sea levels are closely intertwined. Yet, the multiplication of fossils and biomarkers like BRG-DGT gradually allows us to reconstruct the intimate history of the Eurasian oceans. The clues compose a detailed portrait of the ultimate oceanic chapter of the Triassic. It is time to turn this page and let geological times pave the way for new challenges and evolving ecosystems. We are at the very end of the Triassic, between 208.5 million m, or 129 miles mi, and 201.3 million m, or 125 miles mi, years ago. This short but intense period marks the tumultuous end of the Triassic era. Paleontologists study this phase because it reveals how some life forms survived upheavals while others disappeared. To understand these last million years, one must imagine varied ecosystems. Wet plains cracked by tectonic fissures, forests of ferns and conifers, and marine areas where still strange creatures evolved. At this time, the Earth experienced strong climatic fluctuations and major ecological transformations. The fragmentation of the supercontinent changed the distribution of seas and lands. Temperatures varied by region, with progressive warming in some areas, while others experienced intense precipitation or milder periods. The Eurasian rock formations, rich in distinctive fossils and chemical markers, allow geologists to reconstruct this environment over 200 million years old. In this changing context, the crocodilomorphs, ancestors of modern crocodiles, show great resilience. More varied than today, some live in coastal environments, others in lakes, rivers, or marshes. Their thick armor and powerful jaws allow them to hunt a wide range of prey. Their ecological pragmatism is remarkable. They can move on land or in water, hunt fish, terrestrial animals, and carrion. This adaptability makes them particularly resilient in the face of their rapidly degrading environment. Another group that overcomes the challenges of the Radian is that of dinosaurs, already diversifying. Although often associated with more recent times, they have existed for several million years, often being small in size. Theropods, bipedal and carnivorous, stand out for their agility, while others, more massive, are herbivores. Their light skeleton and active metabolism give them an advantage. Adaptable in their diet, they colonize plains, forested slopes, and marshy areas, finding their place despite a changing environment. In the seas of the Eurasian, the fascinating Atopodentatus stands out among the aquatic reptiles. Its flattened, sometimes segmented snout has intrigued researchers, suggesting an original diet. Some think it feeds on algae or small organisms from the seabed. Its presence until the last Radian substage is evidence of an evolutionary experiment at the very end of the Triassic. This creature proves that specific ecological niches persisted despite intensifying environmental disturbances. To study the end of the Triassic, scientists go to St. Audrey's Bay in the United Kingdom. There they examine strata rich in invertebrate fossils, pollen, and spores, stacked in successive layers that tell the geological story. The Eurasian section is well identified, offering a precise chronology of ecological changes. University teams conduct coring, collect rock samples, and analyze their chemical composition, enriching our understanding of the transition between the Triassic and the following period. A recent dating conducted in 2025 using the lead method sets the end of the Triassic at approximately 201.30 seconds, 0.04 million years, or 201,300,000 40,000 years. This result precisely delineates the beginning of the next era. Researchers measure the amount of radioactive isotopes in certain minerals. Their regular decay allows for the dating of rock crystallization. This advancement reduces the margin of error from previous measurements and facilitates comparison with other global stratigraphic sites. Without entering the next period, this milestone constitutes a key step for geology on a planetary scale. Why did certain groups like crocodilians and dinosaurs survive the upheavals at the end of the Triassic, while others disappeared? Researchers suggest several reasons. First, their robustness with a wide diversity of habitats and diets allowed them to withstand resource loss. Next, a resilient physiology, perhaps linked to rapid growth, gave them an advantage against environmental stress. Finally, they likely benefited from territories opened up by the partial extinction of competitors. These combined factors favored their survival during this critical period. The fate of Atopodentatus is also revealing. Until the final moments of the Rhaetian, this marine reptile swam and grazed, according to some hypotheses, in sometimes hostile waters. Its anatomy reveals a specialization adapted to an unstable environment. Its remains provide clues about its nutrition, marine locomotion, and adaptation to benthic feeding, i.e., on the sea floor. It is one of the last representatives of a fauna capable of withstanding changing salinity, low dissolved oxygen, temperature variations, and chemical disturbances caused by volcanic outpourings. The end of the Rhaetian marks a profound transition in the biosphere. On continents, vast conifer forests gradually give way to plant formations better suited to the climate. In wet areas, sediments reveal seasonal flooding, while trunks, spores, and pollens testify to vegetation evolution. Near ancient shores, fragments of skeletons show the cohabitation of terrestrial and aquatic reptiles, proving life in mixed habitats. Thus ends the Triassic, ushering in a new era full of promises.